we're on pages 129 and 130. We'll be looking at more exponential and logarithmic modeling, in particular looking at a half-life formula today. Make sure you have your calculator. The half-life, lowercase h, is the amount of time required for the amount of something to decrease to half its initial value. And the exponential decay function can be written as a half-life function. We'll begin with an example from our first lesson in this unit. The population of a town is decreasing by 4% per year and started with 12,500 residents. Write a function to model this situation. Well, this is our decay model. Capital A equals lowercase a times 1 minus r to the t. Lowercase a is our 12,500. 1 minus r is 0.04 to the t. Algebraically determine when the population of the town will be half of the initial population. Round to nearest tenth of a year. Well, half of 12,500 is 6,250. So 6,250 is equal to 12,500 times 1 minus 0.04 to the t. And we are solving for t, which is an exponent. We want to get that base and exponent by itself. Divide by 12,500. Over 2, 1/2 is equal to 1 minus 0.04 to the t. Now switch to log form. Log base, well, 1 minus 0.04 is the same as 0.96. Go to the calculator. Log base 0.96 of 1/2. Rounding this to the nearest tenth of a year. 16.9797. That's going to round to the 9 is going to round up to 17.0 years. To rewrite A as a half-life formula, we start with the exponential decay formula. Since the amount decreases to half its amount, the R value is 50%, or R equals a half, over the time span of half the life, lowercase h. The annual decay rate is 1 minus 1/2 raised to the 1 over h, or 1/2 to the 1 over h. To calculate the capital A remaining after t years, raise the annual decay rate to the t power. Thus we have 1/2 raised to the 1 over h raised to the t gives rise to 1/2 raised to the t over h. We multiply those exponents there, and 1/2 times t is simply t over h. So here's our half-life formula. For an initial quantity, a sub 0, that is decreasing at an exponential rate with a half-life of lowercase h. So whenever you're given the half-life, that's your lowercase h value. The amount capital A left after t time units is given by the formula. A equals a sub 0 times 1/2 raised to the t over h. Let's write that again. Half-life formula. A equals a sub 0 times 1/2 raised to the t divided by h. Write the half-life formula for the population of the town in exercise number 1. So the initial was 12,500 was the initial population. half-life would have been 17 years. So lowercase h is 17. T divided by 17. The decay of a sample of 5,000 grams of carbon can be modeled by the equation C of t equals 5,000 times 1/2 raised to the t divided by 5,730, where t is measured in years. What is the half-life of carbon? The half-life is this right here. This is our h value, 5,730 years. How can we tell this is a half-life equation? The base is a half. Half-life formula. A equals a sub 0 times 1/2 raised to the t divided by h. One of the medical uses of I-131, a radioactive isotope of iodine, is to enhance X-ray images. The half-life, lowercase h equals 8.02, is 8.02 days. A patient is injected with 20 milligrams, determines the nearest day. The amount of time needed before the amount of I-131 in the patient's body is 7 grams. Okay, so this is capital A, the 20 is a sub 0. Half-life formula, A equals a sub 0 times 1/2 to the t divided by h. 7 equals 20 times 1/2 the t divided by 8.02. We're solving for t, and t is part of an exponent. We want to get that base and exponent by itself, so please circle that. Divide by 20, and 7 divided by 20 is 0.35. We have our base and exponent isolated. So now switch to log form. Log base 1/2 of 0.35 equals t divided by 8.02. Get rid of the division. Multiply. Multiply by 8.02. So we're keying into the calculator 8.02 times log base 1/2 of 0.35. To nearest day, so 12 days. Perhaps if you want to try the next example on your own, pause the video. A given substance has a half-life of 6,000 years. After t years, 1/50 of the original sample remains. Find t to the nearest 1,000 years. Okay, so after t years, 1/5. So we can start with What's our starting amount? You can use any amount you like. I can use 1. And then after t years, the ending amount would be 1/5. And 6,000 is our half-life. Alright, so if we divide by 1, we still end up with 1/5 on the left-hand side. So we have 1/5 is equal to 1/2 raised to the t divided by 6,000. We switch to log form. Log base 1/2 of 1/5 equals t divided by 6,000. Get rid of the division of 6,000, multiply. Go to the calculator. 6,000 times upper window number 5, log base 1/2, 1 divided by 5. To nearest 1,000 years. Okay, so t equals 1,000 years, so the 3 is in the thousands place, right? So this would be 14,000 years. And the last example we're going to look at will actually solve graphically. 2 methods were used to teach athletes how to shoot a basketball. The methods were assessed by assigning students into 2 groups. One group taught with method A and one group taught with method B. The students in each group took 30 foul shots after 10 sessions. The average number of shots made in each of the X sessions, so X sessions, it was from 0 to 10. Using method A can be modeled by, here's our equation, A of x equals 11.90 plus 4.3 ln x. The average number of shots made in each of the X sessions using method B can be modeled by this equation. In which of the 10 sessions to the nearest whole number will the 2 methods produce the same number of made baskets? All right, so in other words, it's asking us for the same number. So when is A of x equal to B of x? Our domain x is X sessions, so our domain is from 0 to 10. And what is the output? The output is the 30 foul shots. The range will be from 0 to 30. How many of those 30 shots were made? All right, so we're definitely, we are not solving this algebraically because we have an ln of x on one side and exponent x on the other. So we have to look at this graphically. So A of x, we'll put A of x into y1, and when we look at the graphing calculator, y sub 1 is in blue, so I'll use blue for A of x, and red for B of x. So keying in a of x and y sub 1, and now b of x and y sub 2. Adjust the window. Our x's, our domain is from 0 to 10. And our range is from 0 to 30. Look at the graph. This is just a very rough sketch. Okay, so here's my blue. This is a of x. When are they equal? So now use the calculator, find their point of intersection. To nearest whole number. Second trace, number 5 is intersect. To nearest whole number, this would be 7.9, which would be the 8th session. And the other intersections, second trace, number 5 again. Enter, enter, but for the guess, I have to move the cursor closer to the point of intersection to the left here. And this would round to the first. So 8th and 1st sessions. Next, we want to find the average rate of change for each method between sessions 3 and 8 for each of the methods. Give the proper units, round to nearest 10th. Okay, we're just going to do one of these. We'll do this for session A. The average rate of change is going to be change in A over the change in X. And for the 8th and 3rd sessions, this would be A of 8 minus A of 3 divided by 8 minus 3. And since A is in Y1, we can look at the table of values. Oh, I'm still on independent. All right. You probably have table set. Yeah, you would likely have this. So 8, so 20.842 minus 16.624 all divided by 5. .8436. To nearest 10th, so this would be 0.8 shots made per session. And we'll stop there. Thank you very much.